Hello, everybody. Welcome to this week's Astro Coffee Hangout. My name is Tony Darnell. I work at deepastronomy.com, and today we are going to be talking about the SOFIA telescope. It is the observatory. We're going to talk about some instruments within that observatory today. SOFIA, in case you didn't know, stands for Stratospheric Observatory for Infrared Astronomy. Basically, it's a JWST in a plane, only way more mobile. So, and today we are going to be talking about some of the instruments and some of the latest science being done by this telescope. And we are hoping that you guys will interact with us on social media. I'm already looking at a lot of you here, and I see a lot. I've actually got some of you being moderators now on the live chat. So thank you for volunteering and being guinea pig for me. I appreciate the extra help. So today, as I mentioned, we have my good friend and colleague, Dr. Carol Christian, who also helps me with these hangouts, and she's going to tell you a little bit about them. So go ahead, Carol. How you doing today?
Doing well. Yeah, it's great to have the SOFIA instrument team's representatives today because it's a really exciting observatory. As an astronomer and a pilot, it's like, that'd be nirvana for me. It would be like perfect. So anyway, the idea behind Afternoon Astronomy Coffee, which are supported by the American Astronomical Society and the American Astronautical Society, the two AASs, as we call them. The idea is that astronomers and often engineers have around their departments or the research organizations coffee, either daily or once a week, where they get together and talk about what's going on in astronomy research, and other sciences do this as well. And we tend to chit-chat about research that we know that's going on. And if we have a guest who's come to maybe give a colloquia, that person is included too when we hear about the research. So we thought it would be great if we could do this online and invite you, the audience, in to talk to some of the people rather than hearing just Tony and I chit-chat about something.
As interesting as we are.
Yeah, fascinating. I know, week after week, we'd lose you. Anyway, so we like to invite people in who are actually doing the work. And today we have instrument builders who are using instruments on this airplane, this beautiful telescope, and they're going to tell us all about it. And so it's very informal. It's not a lecture series. It's really chit-chatting among us. And exploring our own questions as well as the questions from you that Tony will bring up later in the Hangout. So welcome, and thanks for joining us, and I welcome our guests as well.
All right, thank you, Carol. Okay, so we got a lot going on here, so I want to get to it, but we are picking up with our tradition of what we started last week. We are now streaming on both YouTube and Facebook Live /Deep Astronomy. So I'm seeing a lot of you watching on both of those. I'm already seeing people. John Suffel and Yurik Mazino is on the chat. Also, D.H. Blank is saying hi to all the Baker College astronomy students. So hi, guys. Welcome, and I hope you enjoy these. So thanks for showing up. And please leave questions and comments. Soon I'm going to be able to put the chat box in the window here, but I didn't want to mess with it today. So soon you'll be able to see your own chats as we stream as well. So that'll be something new to look forward to. Okay, so we are also looking at, in addition to Facebook and YouTube, I'm also looking at Astro Coffee # on Twitter. So please leave your comments for us there. Okay, so today back to our Hangout. I'm going to introduce our guests. We have 3 PIs from 3 different instruments on the SOFIA Observatory. Joining me in order of right to left on my screen, so I'm not quite sure, is Dr. Matt Richter. He's from the University of California, Davis Physics Department. He is the PI of the XEs. Is that right?
That's correct.
Did I say it right? Okay, cool.
Yep.
Oh, good. So he's the PI of the XE. We'll talk about what all this is, folks, so don't worry about it if you don't get it. Right. Also joining me is Dr. Harvey Moseley. He works in the NASA's Observational Cosmology branch. He is the PI of the 3rd Gen Hermes instrument. Hermes instrument, he clarified, was the 3rd generation of that instrument, right? Is that what you said? No. I still got it.
It is the 3rd generation a 3rd generation instrument for SOFIA, but it is the first of its name, as they say.
Ah, okay, cool. and also is Dr. Darren Dowell. He's a research scientist at JPL. He works in the atmospheric and space sciences section, and he's the PI of the HAWC HAWC instrument on SOFIA. Okay, guys, thanks. Welcome. Glad you guys could all make it. I want to go back to I want to go what each of your instruments do, but I want to start first with an overview of SOFIA, and I wonder if one of you can start. Now, I'll pick one at random if nobody volunteers, but can someone give us a background of just a big picture, maybe a small summary of SOFIA itself? Okay, Harvey. What was it going to be? Matt?
No, Matt.
Matt, are you about to do it? Okay, you
I was about to, yeah. So I always describe SOFIA as a 747 with a hole cut in the side, which gets people's attention at the starting point. So it's an airborne observatory. It's a Boeing 747 that's been modified, and really about a quarter of the fuselage behind the wing has been cut out, a quarter of the circumference. And within that opening, they're able to put in a 2.5 meter telescope. The actual mirror is 2.7 meters, but we use a slightly smaller amount. And with that telescope, we're able to fly up to 45,000 feet and be able to observe parts of the spectrum that you just can't do even from the best sites on the ground. And some of the wavelengths that, well, in fact, I would think all of the wavelengths that Harvey and Darren's instruments work at, they just would be useless from the ground. SOFIA makes them possible and makes that science possible. And it's really the only way to observe at those wavelengths right now.
That's right. How can you give us a sense? How old is SOFIA? How long is it? When was it first launched? First light?
First light was, I want to say, around 2010. Does that sound right to you guys?
About 2010. Okay. And so, how often does this aircraft fly? Is it like Hubble, where you have this time allocation? People apply basically for space on or for observing time on SOFIA. Then you guys decide whose proposals are more scientifically accurate, or not accurate, but worthwhile for SOFIA. Or do you have some other way of deciding who gets to use it? Do you guys know?
Yeah, that's correct. Almost all of the observing time goes to astronomers through a proposal process. So they write proposals typically in May or June. Those proposals are reviewed by scientists, and the ones that have the most merit are awarded observing time for the following year. And those get executed with the instrument suite of SOFIA. So there will be 1 or 2 or 3 week long campaigns with one instrument followed by another instrument. So over the course of the year, all of the priority science programs can be carried out. You asked something about how often. SOFIA flies 3 or 4 times a week during the science campaigns. So it can be a pretty intense experience, pretty exhausting experience.
Oh, okay.
As Matt knows more after having done more flights than the other two of us combined, I'm sure.
Mm-hmm.
I don't know. You're pretty close, Darren, I think.
Okay, so just reading a couple things in the chat, asking me to turn up my mic. I just did. Hopefully it's better. Let me know if you can hear it okay in the chat box. So the observing time that you guys were telling us about, I know that this is something we didn't cover before in the last hangout. That's why I'm asking about it. When you go to observe, obviously you have to be up in the air. It's stratosphere. You have to be very high up in the air. So you've got to be. If you're not flying, you're not observing. How much time does the aircraft spend in the air?
Flights are typically 10 hours long, or a little bit under that. In the initial planning, I think the flight planners aim for around 9.5 hours. And that gives them some leeway depending on what the winds might do. And then when the flight planning process is truly amazing to me. I've got to say it's a lot of work, and there are so many constraints because with this telescope, you can only look at what is off to the, left-hand side of the aircraft and within a certain range.
That's a good point.
Yeah, I had to think about it a bit because I'm usually looking at the back, so the telescope's looking to my right, but that's just a function of where I sit. And you have to come back to where you took off from in almost every case, and there are certain rules for aircraft about where they can fly and how high they can fly, and it causes real challenges. But the final update happens 12 hours ahead of time with improved predictions for winds, and then the flight planners will probably try and stretch it out to up to 10 hours for the total flight. You figure the first 35, 40 minutes might be getting up to altitude, last half hour is coming down, so you might get 9 hours in a really good flight for science. That would be the maximum, I'm sure.
Okay, one more question about this, and I'll move on to the instruments, I promise. Does the aircraft spend a lot of time level, or does it like angle up to get the door up higher? Is there anything weird like that going on? Do you know what I mean? I mean, is it fine to just fly straight and level and it can do its observations, or does it ever have to go in these weird wonky attitudes?
I've heard of people trying to contemplating rolling the aircraft a bit to try to give a little more elevation range, but in practice, I don't think that's been done.
I was just curious. That was what, yeah, you'd have to be some kind of really good flying astronomer to be able to handle that too, I guess. Do the astronomers?
No, I can envision what this was. This was the astronomer saying, if we could do this, and the pilot going, I don't think so.
Right. Straight and level. That's what we want for the airplane.
Fair enough. Okay.
In terms of the altitude level, the aircraft does maintain constant altitude for long stretches, and they do that remarkably well. You can just watch the altimeter, and you're staying within a few feet of your target altitude for the hour or two that you're at a flight level. The flight profile does climb over the night in steps. Typically, one starts at something around 38,000 feet. But as the fuel is consumed during the flight, the aircraft gets lighter and can fly higher toward the end of the flight. So that's when you can get up to 45,000 feet. It does depend on
So you plan that in. You actually plan in using up fuel to get higher.
Yes,
that's right. Yeah, it's all planned out.
And now, okay, we're in a segue to getting to the instruments. You guys are an infrared telescope. The atmosphere is the enemy of infrared. There's a few windows where the atmosphere is transparent at certain wavelengths. The near infrared is a good one, and usually it's due to water vapor absorbing a lot of the infrared as it comes in. When you're at 45,000 feet, does that window open up more than what you would see on the ground? Is there more of a spectrum available to you in the infrared than you would have on the ground? Because lesser atmosphere absorption, water vapor, things like that.
Yeah, it's much wider spectral range is available. From even the highest mountaintop observatories, there are narrow windows at, say, 20 microns, and then another one at around 350 microns, and the in between 20 and 350 is pretty much opaque under even very good conditions. And with SOFIA, you can operate over all of that spectral range. Darren can tell you that with Hawk, they have several four spectral bands or whatever that sort of span the 40 to 250 micron region. All of that is unavailable from mountaintop observatories.
And what's the diameter of the objective on the telescope itself?
We use 2.5 meters out of the 2.7. It's the full size of the mirror.
Great.
But a lot of the infrared instruments have to chop, and so they actually wobble the secondary so the beam moves across the primary.
Okay, and that's related to a question that Adam Synergy is asking on the chat, and I want to get this out while we're talking about it. He goes, he's asking, is the SOFIA telescope sitting on or in gyros? Anybody?
Yes. So there's several layers of isolation from the aircraft and also control of positioning. And Matt and Harvey should correct my errors here, but there's a first layer of the vibration isolation system, which I think of as kind of a springy isolation that the telescope rides on, so it doesn't feel every bump of the aircraft. And then there is gyroscopic stabilization, which is good at maintaining pointing for short time periods. It will hold steady on a fixed position of the sky. But then that would tend to drift over time as gyros do. So the third component of the telescope pointing is to use stars. So there's a camera in the focal plane that observes stars at visual wavelengths, and it uses servo control to keep the star in the same place on the focal plane camera all the time by executing motor control of the telescope.
Awesome. Okay, and I hope, Philip W., that also answers your question, because he went into a little bit more. Does the plane compensate for turbulence and a difficult image to take a picture of at the same time? So yes, there's a lot of things going on that Darren just outlined that's going on.
I guess just to add, I should say that despite flying in an aircraft, this telescope can point to arc-second accuracy and hold that position.
I was going to ask about that. So great. That's really good.
One thing that's really amazing when you do fly is if you're going through light to moderate turbulence and you're watching the telescope with your instrument and you're watching things move around physically from your perspective, and then you realize that really it's not the telescope that's moving, it's fixed in inertial space. It's the airplane and you moving around it. And even after a few flights, that's still entertaining to see and think about.
Okay, well, as many of you are just joining the chat, I am making some of you, whether you ask for it or not, moderators on the chat. Galaxy, I just made you one. You don't have to feel obligated, but if you would like to help moderate the chat, I'd appreciate it. You're here every week, and so I thought I would do that, but you don't have to feel obligated. I just made you moderator there, so I just thought I'd tell you that. Okay, so let's get to the instrumentation, since that's why we're here. I don't know which one to start with. I'm just going to pick the one that's at the top of my list. Let's start with Matt, and let's talk about the XE's instrument. And if you want to go ahead and show any of your slides, go right ahead, or I can.
I think I'll try to show a few.
Great. Yeah. Now, XE's. Start by telling us what it means. What the acronym is.
So XE's EXES stands for the Echelon Cross Echelle Spectrograph, which this is a high-resolution spectrograph for what is known as mid-infrared astronomy, mid-infrared wavelengths. That goes from about 5 to almost 30 microns, is how I usually define it. You can see the picture of, that was our team in 2014. It's a small team. That was most everyone. And we're standing, this was after our first mount on SOFIA. The telescope itself, you can see some of the blue structure in the background, and then the bulkhead is the large kind of cream-colored structure in the back going across the fuselage of SOFIA, the cabin of SOFIA.
I think it's really
and good. The 747's a big aircraft.
I know.
Our instrument is liquid helium cooled. We go to 4 Kelvin. I'm going to say only 4 Kelvin because of the guys who are talking later. And then I guess I'll just scroll down a bit about what the data look like. So we're a high-resolution spectrograph. We have 2 main modes when we're taking science data. Over here in the upper left is our cross-dispersed high-resolution mode. In this case, we're in the lab looking at acetylene gas. This is near 13.7 microns. And all these black features are different lines of acetylene, and we're able to separate the individual lines quite clearly, even though they're quite close. X's can separate light to 1 part in 100,000 in this mode. And
so
then in the upper...
I just wanted to interrupt for a second. For cross dispersing means if you have, say you have a spectrum, like you take a prism and you have the light in the rainbow all spread out. If your detector is small, what you can do is you can fold it, and that's what's being done here. It goes, say, from blue to red, but then you would chop it up into pieces and then stack it up so you can get all of it on one detector, and that's what cross dispersing is about.
Yeah, maybe I should have explained the upper right is more like just a prism with a rainbow. This is a single order or medium resolution, and it's just, this is again acetylene, and the long wavelengths are over here on the right, and the short wavelengths are over here, and this is a small chunk of the spectrum, and each one of these lines is basically a picture of the entrance slit to the instrument. And in cross dispersion, it's flipped a little bit, but the wavelength increases across. But then each one of these different sections is another order from the grading, and it ends up, you get more wavelength coverage that way at this high resolution. So that's, I think, because we're probably not really full on time, I'm going to stop right there and let somebody else go.
Okay, all right. How about you, Darren? You want to give us a little look at some of the things you're working on?
I'd be happy to. If you could show the slides, that would be appreciated.
Sorry, I
have a little
about that.
trouble with the screen sharing.
Hang on, let me get it up here.
And will I see them on my screen when they come up?
You should see it in my thumbnail. Am I on the right one?
Okay.
Yes, Hawk. So just click on my thumbnail, and you should see what I am sharing.
Yeah.
Okay, I'm waiting for that to come up. I'm a few seconds behind, I think.
Okay.
You've got the wonderful Palmdale Wi-Fi.
That's right.
Is it notorious or?
Well, it's adequate for many needs, but not all needs apparently. But
okay.
So I still don't see what people are looking at. But
well, I've got the title page. Maybe try. Well, if I tell you to refresh the browser, you might get kicked out of the thing.
So I'll just.
Well, try clicking on another thumbnail and then back on mine again, and see if it refreshes that way. So just click on say Carol, and then back to me. Do you see it now?
It came up briefly. Okay, there it is, right there. Yes. Okay.
Good. All right.
Good.
Wonderful. So I'm looking at your title page now. So why don't you tell me where you'd like me to go?
Okay. Let's stay there just for a second.
Okay.
Thanks everyone for putting up with my technical difficulties.
But believe me, they are so used to the technical difficulties on these hangouts. They're real troopers. These guys.
Yeah. So I'm working on an instrument called Hawk Plus, and Hawk is for high angular resolution wideband camera. It is a far infrared camera that works at wavelengths from 50 to 250 micrometers or microns. So these are wavelengths 100 to a few hundred times the wavelengths that we can see with our own eyes. And one of the things that Hawk does well is to make images of dust emission. So nebulae where stars are formed have copious amounts of dust, and we can take pictures of that. It turns out that the dust in these clouds is also aligned with magnetic fields. They're little particles, and they line up with the magnetic field. So by looking at the polarization of the emission in the far infrared, we can also figure out what the magnetic fields are doing. So if you go to the second slide, we'll see an example of one of these nebulae, familiar to many, I'm sure. The Orion
I've never
Nebula.
seen this.
Yeah.
So we've seen it for many years, but recently there's a really spectacular image that came from the Hubble Space Telescope. I encourage people to go find that on the Space Telescope site and download it in full resolution and just scroll around it. It's quite amazing. But anyway, this is a lower resolution rendering of it. But you see this glowing gas in pretty colors, emitting strongly at optical wavelengths. But also there's these black patches and streaks and clouds That's obscuration from dust. So that is this dust is the dominant source of obscuration in the optical, but in the far infrared, it's the dominant source of emission. So it's that stuff that we can see with SOFIA and Hawk Plus. So let's go on to the next slide.
Okay. So here it is.
And here's what Hawk Plus looks like. And perhaps people who see my video frame would also see Hawk Plus in my background. I'm in the Hawk Plus lab.
Oh, hang on. Let me get you highlighted there. Let's see. You got it behind you? Yeah.
Yeah, it's back there.
There it is. Okay.
All right. So, but back in the slide set, that's Hawk Plus mounted on SOFIA. So this is the comfortable side of the telescope in the atmospheric control, the pressure controlled cabin. On the other side of that blue wall is the hole in the aircraft that Matt was talking about. That's where the telescope is. It looks out the side of the aircraft. Okay, let's go to the next slide. Okay, so these are a few examples of activities in the lab preparing Hawk over the last few years to get ready to fly, to get ready to observe with SOFIA. And the thing I think I'll point out right now is in the upper left. So that is our detector. You can think of it as a far infrared camera with 4 kilopixels. So 4 kilopixels may not sound like a lot for
it is the infrared.
Yeah. So most people have their megapixel optical cameras that are quite affordable, but in the far infrared, the technology is not so advanced. So we are using state-of-the-art kilopixel detector arrays that were developed by NASA Goddard, where Harvey's from, and in collaboration with NIST in Boulder, Colorado, and also JPL. And these detectors work best at very cold temperatures. We operate ours at 0.2 Kelvin, so 0.2 degrees above absolute zero. It's turned out to be a bit of a challenge to stay at 0.2 Kelvin for long duration in an aircraft, but that's a story for another day, perhaps.
Okay.
So let's
and
go on to
look at all those connectors.
That's right. That's right.
It's a beautiful camera. Beautiful.
I think. I'm sorry to interrupt there, Carol, but it's 2,000 wires that come out of the instrument that we have to deal with. Okay, next slide.
Okay.
All right, so this is back to Orion Nebula. Again, the HST image. This is a little bit more toward the center of it. Again, this is what it looks like at visual wavelengths. If you go to the next slide, you see what it looks like in the far infrared. So this is a Hawk Plus image from December, and the registration is the same. So the angular size it covers, and then the centering is the same. I don't think we have a flip capability here, but it's kind of interesting to look at. Some features correspond. Some of that dark stuff we were seeing from dust is the thing that emits here, but there's also places that are bright in the Hawk map that are not as prominent in the HST map. So these are probably sources that were behind all the emission in the HST map. So we make pictures in the far infrared, but we also measure the polarization. So the very last slide here is a first look at far infrared polarization measured with SOFIA. And there are little tiny black vectors, little black lines on the map, if you have enough resolution to see them. And those show the direction of the magnetic field in Orion. So we can make maps of that and figure out how the magnetic fields are channeling the flow of gas into regions where stars are forming.
So So hang on, I want to stick on this for a minute. This is the polarized infrared light, and those little arrows show the direction of polarization. Is that right?
Yes. There's a subtlety there that the polarization turns out to be at 90 degrees to the magnetic field direction. So I have to tell you which I'm showing you here. I'm showing you the inferred magnetic field direction. So the little black lines show the direction that the magnetic field goes. But
it's based on the direction of the polarization of the infrared light, and you're able to make that map by looking at polarizers on the telescope and measure the brightnesses at different spots in that image. Is that how you actually determine the direction of the polarization?
That's right. We have basically polarized sunglasses inside our instrument that make it sensitive to polarization in the far infrared. And then we have a polarization modulation device, which is a further tool for measuring polarization accurately. It's a device called a half-wave plate made of crystalline quartz. And yes, so that lets us measure the I guess preponderance of radiation vibrating in one direction versus that vibrating in an orthogonal in a direction which is at 90 degrees.
Right. So you're inferring based on Maxwell and a whole bunch of other people the direction of the magnetic field based on the polarized electric component of the wave. That's right. Is anyone else doing this? This is a map of the magnetic field of the Orion Nebula.
That's exactly right, and it's a relatively new technique.
Sorry, but this blows me away. This is amazing. I didn't know people were making these observations.
Well, I appreciate your excitement. Thank you. but we're not the first to do it. This technique has been around in various forms in the far infrared since the mid 1980s. I think is when that started being measured, and there's ways to measure polarized dust also in the optical, and that goes back further. So that was done starting in the 1950s.
Well, and also in my solar physics days, this is also how they can infer the magnetic field of the corona as well by looking at polarized light from the corona as well. So
that's right.
I wasn't aware that this was being done in nebulae and other places. This is astonishing. Wow.
Yeah, awesome. And our specific technique all relies on this really interesting phenomenon where the dust particles in Orion get lined up with the magnetic field. I guess that didn't have to be, but fortunate for us, it is, and that we can make these magnetic field maps as a result of that.
Cool. So this is I have a question. So the magnetic field comes from the clouds that started to form the objects in the Orion Nebula? Well, it originates in the clouds?
So you need a fundamental magnetic field source to get started, and certainly when we know that stars can produce magnetic fields. There are other sources that can produce magnetic fields. Probably entire galaxies can flow in a way that produces magnetic fields, and who knows, maybe there were primordial magnetic fields at the beginning of the universe. But anyway, once magnetic fields are there, the stars can amplify them, and then once stars have made magnetic fields, when gas flows out from stars, that can carry the magnetic fields with them, and then that gas and magnetic field that's flowing out into space, into the interstellar medium, can get recycled into later generations of stars. So that's the magnetic field that we're sensitive to, is that stuff that's blown out of first generations of stellar and galactic activity, and is now channeling gas flows into the next generation of stars.
All right. Well, before we run into too much time, and I want to get to some comments and questions from the people watching, Harvey, tell us a little bit about Hermes now.
Yeah. Well, Hermes is an instrument that's in development now. We've been working for it. We've been working on Hermes since last September. So it still largely consists of drawings and pictures and things, and is only gradually starting to turn into pieces of hardware that will be assembled around the lab. Let me see if I can give you an idea of why we were, what we're thinking about with Hermes. The purpose, you say, why do you build an instrument? What do you want this instrument to do? And in the case of Hermes, we wanted it to be able to explore protoplanetary nebulae, that is, planetary systems in the early phases of formation where the gas and dust has not yet formed planets and so forth. And the question we want to know is, how does that process actually occur? If you look at the picture that I'm sharing there, you have a disk around a star, and in the part of the disk that's near the star, you'll have water vapor. The water will be in vapor form. And so by looking at that, we can determine the temperature and the amount of water in that part of the system. As we go further out, we can spectroscopically search for the water in solid form outside of what they call the snow line. So we can try to get an estimate of how much total ice there is out there. The mass of the cloud that we're working in can be estimated by the amount of hydrogen present. And it turns out the easiest way to measure the amount of hydrogen present is through measuring a molecule that has one hydrogen atom and a hydrogen of a rare isotope, deuterium. So we'd look for HD. So when we built an instrument that could do the sorts of observations that I'm describing right here. And that is an instrument that could work over the 25 microns to about 125 micron spectral range. And it has to be able to operate as a spectrometer. And as in the case of XEs, it needs to be able to provide a resolution that can measure to up the spectrum, the spectral position of something to about a part in 100,000. And then alternatively, it has to be able to measure the emission from, it's got to be able to measure the shape of the sort of overall broad spectrum. So we need a low resolution and a high resolution mode. So in that way, it's similar to what Matt showed you on XEs. And I have I'm sharing with you now a chart that shows a schematic of the optical system. And we use at the back end on the right-hand side, where we have detectors on the light comes in at the far left through the telescope, and then it gets detected on our detectors at the far right. The last element in the system is a grating spectrometer, but if we go and look from left to right, you'll see that we have two FPIs, or Fabry-Perot interferometers. We are using these interferometric things. We use the interference between two partially reflective mirrors to segregate one frequency from another. And you say, why wouldn't you just use a grating like Matt did? And the answer is, well, to get a resolving power of 100,000 at 100 microns, the grating would have to be 4 times as big as it would have to be at 25 microns, or perhaps 8 times as big as it is at 12.5 microns. And I believe that Matt's grating is already close to a meter in size. So we'd be talking.
It was a meter when warm.
Yeah, and so it would take a truly enormous grating, so it wasn't practical. So this was our way to say, if we do it this way, we can actually find a way to make those measurements. So that's how we're going.
But don't Fabry-Perots, don't they need quite a bit of light to really work? Isn't there a lot of stuff that you're just throwing away off the reflections?
Yeah, you certainly lose the reflected light. So another way to say that is that the Fabry-Perot requires that we have to accumulate the spectrum sequentially rather than getting all the colors at one time.
So does that mean co-adding a lot of individual exposures?
Yes, you have to do different exposures at different ones. But that's the downside to it. The upside is that it is an approach that will allow you to do it.
Well, Matt also hogged up all the meter-sized gradient or grading.
Well,
so.
no, the problem isn't the meter-sized grading. It's the fact it would have to be a 10-meter-sized grading at our wavelength. And that's not happening, I think.
Yeah, the 747 is big, but it's not that big.
Not that big. We need to get a bigger one, and it would have to be a cryogenic one too. So that's a big instrument.
Okay, well, I'm just going to respond real quick to Yurik Mazino's comment about this because we're on it. He goes, wouldn't it be easier for SOFIA if the telescope was set on a remote-controlled drone, perhaps designed to go down even further up into the atmosphere? Well, we're talking about meters-long gratings and all kinds of instruments on here, so I don't think drones are going to be all quite that practical. They have to be
it would have to be an automated. This is all very heavy. I think our instrument must weigh 500 kilograms or something. So they're roughly 1,000-pound instruments. So it's a big drone.
So 747 size drone. Maybe
it's called an air.
Yeah.
The telescope itself weighs 17,000 pounds, or no, is that just the mirror, I think?
I'm not sure. It's heavy, though.
It's big.
Yeah. I have another, just to show you sort of what the instrument looks like. We have in the next chart, I show the vacuum vessel, and you can look inside of it and see the optical bench. There are thermal shields that prevent the radiation from room temperature and from 50 Kelvin from getting down. And then, so all the optics run at about between 3 and 4 Kelvin, and the detectors will operate at about 50 milledegrees. So this is similar, but a little bit colder than Darren's Hawk Plus detectors. This uses a cryocooler. So this is using a two-stage cryocooler that provides a 50 Kelvin shield and a 3 Kelvin operating temperature. And let's see what we got. Okay. Yes. And just to show you, this is how you support it. You have little trusses, and you support it from warm to cold and so on. So you have to do all of this engineering just to get one of these detectors on here. And Darren and Matt can tell you they had to both go through a most excruciating process to actually get the instruments on the plane, and I'm looking forward to that. So.
Oh, I'm sure you are, Harvey.
Okay, and now just
yippee!
Let me go to another thing. One of the real distinctions here is that at the wavelengths we're working at, normally it's hard enough when you have to go out and design and build an instrument with so many pieces. At these wavelengths, you not only have to design your instrument, but you have to design and build your detectors too, because there really are no commercial sources for detectors of appropriate performance at these wavelengths. So one of the first things we did when we got selected to build the instrument was to start turning out the designs of detectors that we wanted. So here on the left, you see this nice rectilinear grid of detectors. That's our first grid of detectors for the low resolution mode. That's for looking at the water ice features in the continuum. And then on the right are some test devices. And we've looked at these now, and this is what it looks like on the bottom. That's what it looks like when it's hooked up to all of its superconducting readout electronics. And then we've actually gone further and measured noise and all sorts of properties of our devices, and they're looking pretty good. So we're getting through the first gates now, but there are many, many more gates to go. But we're looking forward to being on the plane roughly 2 years from today.
Okay, that's going to be my next question. Okay, so in about 2 years, you'll be on the plane.
Yes, sir.
Wow.
Is there enough room on there for everybody? I mean, does anybody have to get off to make room for a new instrument?
Only one at a time.
Just one at a time. So you've got to have a system in place for getting these things off and on multiple times then, right?
Yes.
Oh, that's
Yeah,
cool.
it takes about 3 days right now to do a full instrument change.
And presumably you're going to have an observing run with that, right? So you've looked at all your proposals and you're going to say, okay, here's all the science proposals that would require this instrument. We're going to go ahead and run these all in a row, and then you do another switch over and things like that. That's another advantage of being in a plane on the ground, because you can do that. That's really cool.
Right.
That's right. And the instruments get on the plane the same way that people do conventionally on a 747. There's no extra holes, so we have to build instruments that will fit through the aircraft door. It's the same one that the people go through.
I'm going to say it. I probably shouldn't, but hopefully they don't get taken off in ways that people do.
Yeah, right.
Only if they behave badly.
That's right. That's right. Oh gosh, I just had to do that. Okay.
Yeah.
So I want to get to a couple more comments. Let's see. Stephen is asking, and this is like way in the future, but we've been talked in the past on this Hangout series about star shades, and the star shade is this big orbital occulter, for lack of a better word, that is really beautiful. It's a petal shape, and it's designed to block out stars' light so that we can see the things that might be around the star. And Stephen Rapoli is asking, I have proposed for years, is it possible for SOFIA to chase a shadow of a star shade in a Molniya orbit? I'm not sure what that is, but
Those high inclination
good.
orbits like the Russians use for the communication satellites.
Oh, thank you, Stephen. I learned another new thing. I love doing these hangouts. I learned stuff. I didn't know there was a for that. Okay, so I know that there isn't any being built right now, but could it conceivably be possible for SOFIA maybe to hide behind a star shade and do some observations? You guys are quiet.
Yeah. Well, no, go ahead, Darren. I don't want this one.
Okay, I was gonna avoid the question by answering it a little bit differently, because I don't know much about star shades, although I know they're a hot topic and of a lot of interest because of the things that they would let you learn. Mm-hmm. However, SOFIA does chase shadows already,
right?
And these are not artificial star shades, but there are asteroids and planets that occasionally go in front of stars, and SOFIA does go chase those down. They're known in advance, and so SOFIA can plan flight plans for them, and a couple of instruments have observed through these shadow events, occultation events, the HIPPO and FlightCam instruments that weren't featured today, but expand the SOFIA capability. And by observing the timing in detail as the asteroid or planet passes in front of a star, one can learn about things like atmospheres, for example, of the asteroid or planet. So I guess it's in some ways similar to the star shade idea, and something we can do already.
Good. Okay. Well, Stephen, I just want to say that's a great question, but you're way far ahead. Right now, you know where star shades are? I think Northrop Grumman has built one about this big, and they've put it in the desert on a tripod, and they did some tests using bright lights and cameras and telescopes to see if they could see another bright light really next to the star shade. And they're still testing the concept, but to get it in orbit is quite a bit further down the way.
But also, I want to comment that the star shades that are being talked about in NASA are orbital, and so it's not like formation flying in suborbital in the Earth's atmosphere. It's very different having two aircraft, one with a telescope and one with a star shave, coordinating, all the kind of turbulence and all that you get. In space, you don't have all that, so you're just like making little tiny corrections while these things are in orbit. So it's a very different flight problem.
And they're also considering those, I believe, largely in solar orbit, correct? Because I think he was talking, the caller was talking about perhaps a highly elliptical Earth orbit for the star shade, but a suborbital thing. And I think it might be hard. I'm sure that there would exist some place that you might be able to do that, but then you have to make sure that it would also have to be looking at your most favorite object ever at the same time. So that's a lot of coincidences going on there. Very tricky.
Okay, well, still is a great question, though. So I'm going to lump one question up here or two comments into one question. Philip W. and Joe Schmo are asking, can SOFIA be used to map objects in the solar system, such as gas giants in the infrared? And Joe Schmo followed up with, or maybe even find Planet 9. Guys?
So certainly SOFIA is good at looking at solar system objects. We've got a paper that we've submitted on Mars and looking at its very tenuous atmosphere, where we were searching for methane on Mars. And I think at the longer wavelengths that Darren and Harvey are looking at, well, especially Darren, I'm guessing a lot of the planets are more perhaps calibration objects for you. So they're known objects that you can use to test the instrument and know exactly how your instrument's performing. Harvey, I'm guessing you're going to be able to do some high-resolution spectra of planets that'll be quite interesting.
We are. One of the things that we're interested in is understanding the isotopic ratios of hydrogen among all the giant planets, and so that you can tell the ratio of hydrogen to its heavier sibling, deuterium, and this has been measured, but has not been perhaps measured in a completely uniform way among all the giant planets.
Okay. Philip W. has a question for you, Harvey. He's asking, has NASA got a selected list of potential protoplanetary disks yet?
Yeah, there are published disks, published lists of disks around their papers out on that. I don't think I have it in front of me here right now.
But you're not gonna put this thing in not knowing what you're going to look at. So.
No, they're objects. They're objects of known brightness. We were trying to go after the sensitivity limits that we set for ourselves were largely dictated by the fact that we wanted to be able to go after known disks that are around solar type or solar mass stars. So we'd like to look for things around the one solar mass star.
Nice.
And there are enough of those nearby to do it.
Awesome. So James Klett is asking a really cool question. I want to get this in. What is the cost difference over time of flying this in a plane versus placing it in space/orbit? Is that a factor, really, the cost of flying versus putting it in orbit? In fact, why even put it in orbit? Why not just, put it in a plane? Why not put it in orbit?
I think you go back to the mass is a big factor. Right, my grating is a 1 meter chunk of aluminum, my primary grating. And even when you lightweight it, it weighs 32 pounds. And trying to get 32 pounds in space, I'm not sure of the real cost per kilogram, but that's just for one part of the instrument. These instruments weigh close to 1,000 pounds. So getting 1,000 pounds into orbit is not going to be cheap. Harvey, I'm glad to see you nodding your head in agreement.
I think that that's one issue. Another issue, which is another potential advantage that SOFIA has over flying in space, is that for a particular type of science, having a mission in space is really a generational prospect. You're only going to see that once in a generation, and so what SOFIA allows is for new ideas, new technologies, new science to be tried, and lets you do the legwork and develop the new science, develop the new technologies, support the community while you're waiting for lightning to strike for that generation.
All right. So Andrew Planet is on Facebook. I want to get his question in. I'm sorry about my microphone volume. It keeps turning itself down. Andrew Planet on Facebook is asking, with the age of space planes dawning, will observatories like SOFIA be going further up in the sky? Do you anticipate, with these newer planes that are being built, perhaps to maybe have higher altitude observatories like this?
It would be.
It would be nice.
It would be nice. But those are. I don't think any of those planes are as big as the 747 right now,
Yeah.
and the size actually is important for this sort of work, I think.
Okay.
Yeah.
Yeah,
I mean,
I guess go ahead, Matt.
Well, I was going to bring up balloons as a next step, or a technology that NASA is developing, and you're getting to have more capability from high altitude balloon flights. It's not quite to the mirror size that SOFIA is, and astronomers always want bigger mirrors. But it certainly, I see it as an interesting technology that hopefully I'll be able to take advantage of sometime.
I'm glad you mentioned that, because that was something Hans Milling was asking about, using balloons. So thanks for commenting on that. I appreciate it. Okay, well, I think this is most of the questions. We're almost out of time, so I want to thank my guests. Oh, and I didn't do my introductions like I usually do. You are watching the an Astro Coffee Hangout with members of the SOFIA team. We have 3 principal investigators for 3 different instruments. I have Dr. Matt Richter. He's from the University of California at Davis Physics Department. He works on the XES instrument. Also is Dr. Darren Dowell. He is a researcher, scientist at JPL. He works in the atmospheric and space sciences section. He's a PI of the Hawk instrument on SOFIA. And also, finally, Dr. Harvey Moseley. He works on the NASA's Observational Cosmology branch and is the PI of the Hermes instrument on SOFIA. So thank you all so much for taking time out to tell us what you guys are working on, and I hope you'll return us, as you guys are getting more data and information, and as these things become more, part of the operations of SOFIA.
Thank you.
Thank you.
Thanks very much.
My pleasure.
Okay, well, I want to thank all of you guys for watching. And thanks for noticing that the quality's gotten a little bit better. There's a lot of things that I can do that I'm going to start doing now that I've tested this technology out. Some of you have already noticed that I have 2 different cameras. This is one camera, but if I use this camera, you can't hear the guests. So that's why I didn't use it that much. But I also have this one. This one's mirrored, and this one is not mirrored. So that you already guys noticed that. I'll get all those little kinks worked out. But you believe me, that getting it this far was huge. So thank you guys for commenting and sticking with us and being a part of this hangout. The quality will only hopefully get better with each hangout instead of having these problems like we've had in the past. So thank you all very much. Next week we are having the Future in Space hangout, and I don't have any idea what it is yet. Harley hasn't. I think he's still working out the final.
That's a secret.
It's a secret. So we'll be back next Thursday, 3 o'clock on both Facebook, facebook.com/Deep Astronomy, and on this YouTube channel as well. I'm probably going to get rid of my live page for a while, just because you guys were really great at moderating the comments today. Thank you guys for answering the call. It really made the live chat here a pleasure to read. So thank you for participating with me and making the chat a little bit better. All right. Well, on behalf of Carol Christian, Carol, thank you for setting this up, and I want to thank all of our guests. Thank you all so much for taking time out to be with us. Thanks all for watching, and as always, keep looking up.
Thank you so much. This is great.
Thanks.
Thank you.
Okay, bye-bye.